Hi, I'm Gary Rubenstein, and this is the 14th part of a series of videos that is math teacher, me, taking you through my thoughts on school math, starting in kindergarten and working my way up until about 10th or 11th grade trigonometry. Oh, it's a part 14 where the last few videos have been about algebra, like Algebra 1. And if you took Algebra 1, or you're taking Algebra 1, or you're going to take Algebra 1, a thing that people sort of remind, when people think of algebra, they often think of these graphs. Things like this. Pictures where you have this graph paper with these 10 by 10 grids, and you have these shapes on them, lines or these U-shaped things or circles or unusual curves. And this is a big part of algebra. And in this video, I want to show you why is this important, why do we do it, and what's it all about. So we'll get into this. When you have a algebra equation like, for instance, x plus 2 equals 10, well, that has a solution set. There is a single number that makes that equation true. The solution set is the number 8. And we solve it with algebra, subtract 2 from both sides. And if we wanted to show what that solution sort of looks like, we could make a number line. And on that number line, if this is 0, and here's 8 over here, we can make a single dot on the number line to show that that equation has just one answer. But if I were to change the equation, so now it has two variables, x plus y equals 10. And we saw this in a previous video with systems of equations. Now there's not just an answer, but there's infinite answers, and each answer is no longer a number, but it's what's called an ordered pair. 2 plus 8, and it's an ordered pair because 8 comma 2 counts as another solution to this equation. And there's an infinite number of them. I'll just pretend 0 there, but you could also have, they don't have to be nice integers. You could have like a half, comma 9.5, or you could have like -3 plus 13. So this solution set has infinite number of ordered pairs in it, compared to this one that only has a single number as its answer. So to visually show the solution set to the first equation, it's a dot on a number line. Kind of boring. To visually show the solution set to this equation with two variables, we're going to need a lot of dots, and they're not going to fit on a number line. Instead, we put them onto what's called a coordinate grid. And the way this works is these axes, I'll call the horizontal the x-axis, and the vertical the y-axis. I could put arrows on both ends because this thing goes on forever in all these directions. So when I take the equation x plus y equals 10, and I take each of the ordered pairs, for instance 0 plus 10 is 10, and if I make the first number the x-coordinate and the first number the x-coordinate and the second number the y-coordinate, I end up with a single dot right here. This dot represents the ordered pair 0, 10. And 1 comma 9 also is a point in the solution set, and that would be a dot here. And 2 comma 8 is another one. And when I make them all, you start to realize that they're not just a bunch of random points, but they form a straight line. And this is just 11 of the points. But if I were to connect the dots, it seems pretty obvious that it would keep going. It's not just the dots between these, but it's the dots that keep going, plus the dots that are between the other dots. Like, for instance, 1/2 comma 9.5 maybe is over here. So this line represents a picture of the solution set to this two-variable equation. And that's what these graphs are. And the more complicated the equation is, the more complicated the graph might look. Here's a bunch of them. Now, there's two ways that these graphs are used in algebra. One is like a really abstract thing, like visualizing solution sets to equations that have two variables. And that gives us some insights into the equation sometimes, like in this equation, y equals x squared minus 1. Just the fact that there's like multiple numbers that have the same y value, that's like something that you might not realize when you just look at the equation. So there's that really abstract idea where you just get an equation and try to draw a picture of the solution set for it. But the second use is of a more practical nature, because graphs, especially when the x-axis represents like time and the y-axis represents something, in this case like distance, this picture isn't really, it could be an equation that it's representing, but this is representing like a real life situation where each dot tells you something. Like if there's a dot here at 4,3, it's telling me that, 4 minutes into my trip, I had traveled a distance of 3 feet or whatever it was. So the dots themselves could represent things in the real world. So that's what's kind of funny about graphs. You've got the really abstract idea of, oh, I could take any equation and turn it into a picture. Maybe I could take a picture and turn it into an equation. And then the real practical thing that in the real world, in science, you might have, like, for climate change, you might have, temperature on the earth and you start seeing it rise over the years, things like that. Or you might see amount of polar ice, and you see it sort of staying the same, and all of a sudden you see it like going like that, and you say that's bad. And then all of a sudden you see it going like that, and you say that's really bad. So in science, we can represent data in a graph, and looking at the graph tells us more information than like just looking at a table of numbers. But in this video, I want to talk about both aspects, the really abstract one and the practical one. I think I will start with the abstract one. A very common equation would be something like this. What if y equals something x? I'll say 2x plus 3. So this equation tells me how x and y are related. And if I want to know the solution set for it, unlike the last one, which was x plus y equals 10, it's real easy to just think, oh, what two numbers add up to 10? In this one, you might make a chart and say, okay, well, what if x was 0? And then you would come here and say, well, then y would be 2 times 0 plus 3, which would be 3. So that would be a member of my solution set. And what if x was 1? Then y would be 2 times 1 plus 3, which would equal 5, if I made a dot there. And what if x was 2? Y would become 2 times 2 plus 3, which is 7. And it seems like I could just make up any number I want for x, pop it into the equation, out would come a value for y. And when an equation is of this form, y equals something x plus or minus something, it's known as a linear equation. And the graph of the solution set will become a line. And that's one of the simplest graphs there is. Now, this equation could just be this abstract thing, just points, ordered pairs that make this equation true. But it could be something that's, it could be related to the real world. Like the x and y could represent people. Like maybe there's some water that we're filling up. You know, there's like this large can, and it has currently the water level is at 3 inches when this starts. And then we're pouring water in at a rate so that the amount of water, the water level rises by 2 inches every hour. Well, in that case, in the real world, we wouldn't have this stuff anymore because we're not going back in time. But if this is like time, and this y-axis is water level, this, it's called a ray when it starts at a point and goes on forever in one direction. That ray is a picture of what's going on in this situation here with the big tub of water that started with 3 inches of water, and the water was going up by 2 inches every hour. And, you know, the expression, a picture is worth 1,000 words. Well, this picture may not be 1,000 words, but it is, I guess it depends what you count as words, because there are an infinite number of points on this graph. Like 0, 3 is here, and 1, 5 is here. So this picture is telling us a lot. It's saying at 0 seconds in the beginning, there's 3 inches of water. And at, 1, let's just say hour, 1 hour, there's 5 inches of water. But it's also telling us in between how much there is. And also the points themselves tell a bit of a story, because you look at the all the points together and you see, okay, there's a trend where the line is going up at some kind of a steady rate. If you have both the equation and the picture, you could use the picture to answer questions about the equation. Like I might say, what happens when x equals 3? What's y? Well, I could go to my picture here and go over 1, 2, 3, and go up and locate, what is the y value. And I look over here, say, okay, it looks like it's up at about 9. So the picture can help us answer questions about the equation. On the other hand, the equation, if I say, I wonder what happens at x equals 4.3, and I can't really, here's 1, 2, 3, 4, 4.3. I can't get a really precise answer from the picture. But if I take the equation and I put 4.3 in for x, I get y equals 2 times 4.3 plus 3, which is 8.6 plus 3, which is 11.6. So the equation gives me information about the picture, and the picture gives me information about the equation. The picture on its own, like looking at, just glancing at the picture, tells us that the ordered pairs sort of go up and up and up. You might get more complicated equations where things go up and then come back down, things like that. So that's just a general idea of what we do with equations. We can use the equation to predict what's going to happen later on this line and we can use the lines to talk about the equation. So there's a relationship between those two things. And that equation might not just be this relationship between this random abstract x and y, but those two things might represent, water level and time instead of x and y. That y equals 2x plus 3 equation is a specific example of a linear equation. But in general, and here's something, if you took math already, this will bring back memories for you. Y equals mx plus b. Y equals mx plus b. That's a lot of variables, 4 different ones. This is basically a way of talking about equations of this form, but we're not like saying what m and b are at this time. So like y equals 3x plus 2 is an example of that. Y equals 5x minus 1 counts. Even though this says plus, b could be negative. Y equals negative 2x plus 3. M could be negative. So in an equation that has this general structure, there's going to be a y equals, there's going to be an x with a coefficient in front of it, and a number afterwards that's a constant. And all of these things, so for this one, m is 3, for this one, m is 5, for this one, m is negative 2. And b is plus 2 for this first one, b is negative 1 for the second one, b is 3 for the third one. So this is linear equations, and you often hear y equals mx plus b, which sort of rolls off the tongue. When an equation is of this form, the m, the coefficient, the number attached to the x, tells us something about whether the line, how steep the line is. Because you have different types of lines. You could have lines that are very, sort of not very steep. Like if you were on roller skates, it would be very easy to go down this one. Versus something like this, where if you were on roller skates, it would be a lot harder, so it's so steeper. The steepness is related to this number here. And I think I want to start with ones where b is 0. Those will be the easiest to analyze. So like y equals 1x plus 0. Well, that means x and y are the same number. So 0, 0 would be a point on it, 1, 1, 2, 2, 3, 3, and so on. Let's compare that in red to y equals 2x. That 2x also has 0, 0 on it. But when you put 1 in for x, y is no longer 1, but it's 2. And 2 goes in for x, y is 4. And for every time x goes up by 1, y goes up by 2. Oops. What we say is that red line has a steeper slope than the black line. And the slope, the definition of slope, and slope's a word you hear a lot in this type of math. The slope is a measure of steepness, and officially it's for every unit that you go, if you go on this line, this red line for instance, you go to the right 1 unit from where you are, how high up do you have to go to get to the next point? And it's 2 in this case, over 1, up 2, over 1, up 2. But it's 1 in the first case, over 1, up 1. So the slope is actually the coefficient, the number in front of the x. So for this y equals 2x, the slope is 2. For y equals 1x, the slope is 1. And m is known as the slope. And so when we see an equation like y equals 5x plus 3, the 5 is the slope. And A slope of 5 is very steep because for every 1 unit to the right, you go up by 5 units, and you get a very steep thing to roller skate on. Now, when there's a number, a b, that's not 0, I'll go green now, y equals 2x plus 3, let's say. Well, if I put 0 in, I don't get 0 anymore, but I get y equals 2 times x, which is 2 times 0, which is just going to be 0. So when x is 0, y is going to end up being whatever the b value is. In this case, it's 3. And what that does, so I have a point here, 0, 3. But if you put 1 in for x in this green equation, you get y equals 2 times 1, which is 2, plus 3, which is 5, which is over here. And notice that the slope of this green line is still 2, because when I increased x by 1, the y value went up by 2, because that the new x got multiplied by 2. So if you add 1 to something and then double it, it's going to be 2 more than the original thing. And that red line and green line are parallel. They have the same slope. So we have a way to tell if two graphs are going to be parallel based on whether their slopes, whether the m value, whether this coefficient in front of the x is the same or not. This b value in y equals mx plus b is known as the y-intercept, because it is the place where the line crosses the y-axis. So this leads us to a bit of a shortcut for creating the graph of an equation that has the form y equals mx plus b. We start with this, which is the b value, and that tells us that the y-intercept is 0, 1, which means we can put a dot right here. Then the number in front of the x is the slope. It tells us that for every 1 unit to the right, you have to go up by 3 units. That's how steep it is. So from this 0, 1 point, I go 1 unit to the right, and I go 1, 2, 3 units up. And that's going to be my second point. And you can just connect those. You'd be done, but I like to make another point. Those points are all going to fall on the nice same line, but it's good to have 3 points. It's easier. You get a little more accurate. So that's a really famous thing from math, graphing linear equations, y equals mx plus b form. You could also go in the other direction. You could have a picture, this red one, and you can want to know what's the equation. Well, since it's a line, it's going to be y equals something x plus, or maybe minus something. And it's just a matter of finding the m and the b. Well, the b is related to the y-intercept, which is 0, negative 1, which means b is negative 1. And for the slope, you could take any 2 points that you can kind of see. I'll just use this one and this one. And you just say, well, how would I get from this point to this point if I wasn't on the line, but I had to go to the right and then up? Well, you would go to the right 1 unit and then up 2 units. So the slope is for every 1 to the right, how much up would you go? And the answer is, in this case, 2. So the slope is 2, and that's m. So the equation is 2x minus 1. Now that I have the equation, I can use this equation to answer questions about the line, like what's going to happen when x is 100? Well, 100's way off this picture, but if I plug 100 into the equation, 2 times 100 minus 1, and I get 199, I'm able to answer questions about the graph with the equation. So the equation and the graph kind of give information about each other. Two special examples of equations are ones that only have one variable, like x equals 5. It's kind of a strange equation, but you'd say, well, that's not like x plus y equals 10 that has all these answers. X plus 5 has only one variable, so it must have just one answer. But since I have this xy coordinate axes here, I want my answers as ordered pairs. So we don't just say 5 is the answer. We have to give a y value. And the truth is, you could put in any value you want for y. So all of these points, it's true that x equals 5. And when you graph them all, you end up with a vertical line, x equals 5. On the other hand, if I say y equals 3, that has numbers like ordered pairs like 0, 3, 1, 3, 2, 3. And when I graph those, I get a horizontal line. Pretty popular question that comes up in school math is to try to, if you're given a picture, to create the equation. And this happens in science a lot. You know, you collect data, and then the data, when you graph it, looks like some kind of picture. Then you find the equation of that graph, and then that equation could be used to predict other things that would happen if the picture continued. So it's used in science. I'll show you that in a bit. But here's like the basic question: is find the equation of this line, y equals, mx plus b. And because this line doesn't, at least we don't see it crossing the y-axis, we can't see what the b value is so well. But we can figure out the slope. If we look here, the 2 points that we know, unfortunately, are not just 1 unit apart, because if they were, we would just see how much it went up for each 1 unit. But in this case, to get from the points I know, 1, 4, to the other points, I actually have to go over 2. 2 to the right to get to 3. This point over here in the corner has the same x-coordinate as the 3. And then I would have to go from 4 to 10, I have to go up 6. So that suggests that if I have to go over 2, if when I go over 2, I go up by 6, if I only went over by 1, that's half of 2, I'd only go up by 3. And the slope ends up being 3. There's a famous equation, m equals, people say like rise over run sometimes, basically means how much does the point have to go up by to get to the next point. In this case, it goes up by 6. And the run is the from left to right, which is 2. 6 divided by 2 is 3. There's other things people say. M equals y2 minus y1 over x2 minus x1. That just means like y2 is like the y-coordinate of the second point, and y1 is the y-coordinate of the first point, and x2 is the x-coordinate of the first point, and x1 is the x-coordinate of, sorry, x2 is the x-coordinate of the second point, and x1 is the x-coordinate of the first point. So we get like a formula there, 10 minus 4 over 3 minus 1. Either way, we get the answer 3 for our slope. Now, we still don't know what b is, but let's just write the equation so far, y equals 3x plus b. We don't know what b is. We can't see it. It's the y-intercept. We don't know exactly. We could probably graph it. But I just wanted to show you that whatever b we pick, we could check if it was right by testing that if I put 10 and 3 in for x and y, would it make the two equations true? So the sneaky trick is you could pick either of these points, 310 or 1, 4. I'll just use the 310. And if you plug in the y value, which is 10 for y, and the x value, which is 3 in this case, and leave the b alone as a b, then we could actually do a little bit of algebra here. And we can solve for b. And that's why the answer to this question, or the equation that goes with this graph, is y equals 3x plus 1. Now, before I get to the scientific applications, I just want to mention over here that more complicated equations get more complicated graphs. Like this one over here, when it has a squared, we end up with this U-shaped thing that's called a parabola. And, for example, if you put like 3 in to this equation, you get 3 squared minus 1 is 8. But if you put negative 3 in, negative 3 squared is also 9. And when you take away 1, you get 8. So you get this kind of odd behavior where it makes this U-shaped thing. It just, because negative numbers become positive when you square them. And there's a lot of times in real life, especially with like gravity, where the path of a projectile becomes this upside down parabola. This equation has x squared and y squared, and it ends up becoming a circle. Because 5 squared plus 0 squared is 25, 0 squared plus 5 squared is 25, negative 5 squared is 25, so I could have these 4 points. But if there's some other pairs of numbers, for instance, 3 times 3 is 9, and 4 times 4 is 16, and those add up to 25 also. So there's other points, and it ends up becoming a circle. And you could even have this kind of situation. Find two numbers that multiply to give me 10. Well, 1 times 10 is 10, and 10 times 1 is 10. But also, 2 times 5 is 10, and 5 times 2 is 10. And if you just look at this right-hand side here, that's something that happens in real life sometimes. As time goes on, there's fewer like empty seats on the subway. You might get like a graph like that if you ignore the left-hand side here. So different equations have more complicated looking graphs. We've only really looked at these straight line ones. That's all I'm going to do for this video. I'm going to finish up with a real life application. So here's like a scientific application. Let's say I plant some kind of tree, some kind of plant that's growing, and I do some scientific measurements, and I notice that after 4 weeks, the plant is 6 inches high. So I'll say weeks. After 4 weeks, it was 6 inches high. And then I wait, and then after 10 weeks, I measure, and it's 9 inches high. And I might want to know, when is this thing going to be, 20 inches? So one way that I can do that is on this graph, I created the points 4, 6, and 10, 9, and I connected them. It grows. We're assuming it's growing at this steady rate. I mean, in reality, it's not going to be a perfectly straight line. So this is just an approximation. To get a more accurate graph, we probably need a more complicated equation. But since this is a line, I'm going to figure out the equation in this y equals mx plus b form. And the m, the slope, I can do 9 minus 6 over 10 minus 4. The idea is that it from 4 to 10 is a difference of 6. So after 6 weeks, it went from 6 to 9, which is 3. So in 1 week, it must go 3 divided by 6, which reduces to 1/2. And that's the slope of this line. And it's basically that has a meaning in the real world. It means that every week this thing grows by 1/2 an inch. And you could test that out. If it's 6 at 4, it's 6.5 at 5, it's 7 at 6, it's 7.5 at 7, it's 8 at 8, it's 8.5 at 9, and it's 9 at 10 weeks. I can take either of these points. I'll just do the 10, 9. And I'll so-called plug it into this equation. 10 equals 1/2 is what I just figured out for m. Sorry, it's not 10 equals, it's 9 equals, it's the y value. 1/2 times 10 plus b. 9 equals 5 plus b. 4 equals b. So that tells me what the b value would be. We don't really need it. We now have the equation, 1/2 x plus 4. And what's great about that equation is it can be used to answer questions between 4 and 10, or what's going to happen later. So now I can take this equation, and if I want to know, well, here, I'll answer 2 questions. What's going to happen after 15 weeks? I can plug, let me make it 16 I'll take 15, no problem. If I plug 15 into this equation that I just figured out, I get y equals 1/2 times 15 plus 4, which is 7.5 plus 4, which is 11.5. Or I can predict when will it reach 20 inches by putting 20 in place of the y value. Subtract 4 from both sides. 16 equals 1/2 x. I like to multiply both sides by 2. And I found out that in 32 weeks, it will be 20 inches tall. So that's like a good use of science. And you collect data, you analyze the data to create an equation, then you use the equation to predict. And that's a good use. So this whole topic is funny because, like I said, it's really practical. Like scientists can use it to create equations based on graphs and then use those equations to make predictions. But in higher math, we also use it just study equations without any practical applications to study the properties of equations because the graphs give us insight into the equation sometimes. So that's what I wanted to show you. I guess the main thing is that if you heard of, or if you, hopefully now when you hear the expression y equals mx plus b, you think, okay, that has something to do with lines, and those lines might be related to things in the real world. Or maybe the graph is just a picture of solutions to an equation that helps us, study that equation in higher math. Okay, I hope you liked that video.